Black holes destroy everything. Stars, planets, light. Nothing escapes once it crosses the event horizon. But here's what should bother you. What happens to information when it falls in? Does it vanish? Can the universe actually erase information? Because if the answer is yes, quantum mechanics breaks. If the answer is no, where does the information go? We say information is lost in black holes, as if that settles it. It doesn't. It creates a crisis. Two of the most brilliant physicists of our time, Stephen Hawking and Leonard Susskind, spent 30 years fighting about this because the answer threatens to destroy either quantum mechanics or general relativity. You can't save both. The problem isn't what black holes do to matter, it's what they do to the laws of physics themselves. In 1974, I proved something unexpected. Black holes aren't actually black. They radiate. Quantum effects near the event horizon cause them to emit thermal radiation, what's now called Hawking radiation. The black hole slowly loses mass, evaporating over enormous timescales. For a stellar mass black hole, this takes longer than the current age of the universe, but eventually the black hole disappears completely, which created a terrible problem. Imagine you throw an encyclopedia into a black hole. All that information, millions of words, thousands of pictures, everything humanity knows about physics, history, biology. The black hole swallows it. Then the black hole radiates. But Hawking radiation is pure thermal radiation. Random photons, maximum entropy, like heat from a fire. It carries no information about what fell in. The encyclopedia's information is simply gone, erased from the universe. This violates quantum mechanics. Fundamentally, quantum theory says information cannot be destroyed, only scrambled. You can burn a book, and in principle, if you collected every ash particle, every photon of light emitted, every gas molecule, you could reconstruct what the book said. Not practically, but in principle. The laws of quantum mechanics are reversible. This property is called unitarity. Evolution must be reversible. Information is conserved. I said, too bad for quantum mechanics. General relativity says the information is lost. Susskind said, no, the information must escape somehow. Here's why both positions seemed unassailable. My calculation was rigorous. I used quantum field theory in curved spacetime, combined quantum mechanics with general relativity, at least in the regime where both are well tested. The mathematics is clear. The event horizon is a smooth surface. Nothing special happens when you cross it. An observer falling into a black hole experiences nothing unusual at the horizon itself. No wall, no barrier, no violence. You cross, you continue inward, you eventually hit the singularity where you're destroyed by tidal forces. But at the horizon? Smooth passage. So the information falls past the horizon, continues inward, reaches the singularity, and is gone, destroyed. Susskind's position was equally rigorous. Quantum mechanics has been tested to extraordinary precision. Never, not once, have we observed a violation of unitarity. Information conservation is foundational. It's built into the structure of quantum theory at the deepest level. If it breaks for black holes, it could break anywhere. The entire framework collapses. One of us had to be wrong. But which? In 1997, we made it official, a public bet. The stakes, an encyclopedia appropriately enough. I claimed information is lost. Quantum mechanics needs modification. John Preskill and Susskind claimed information escapes. General relativity needs modification. The fight lasted decades because both sides had powerful arguments. I kept asking, show me the mechanism. How does information get out? Nothing can escape from inside the event horizon. That's the definition of an event horizon. The escape velocity exceeds the speed of light. So if information is inside, it's trapped. Period. Susskind kept asking, show me where unitarity breaks. What's the physical mechanism for information destruction? Not just, it's inside the black hole. That's not a mechanism. That's a location. What actually destroys the information? Where in your equations does unitarity fail? Neither of us had satisfactory answers to the other's questions. Then Susskind proposed something outrageous, the holographic principle. Susskind's radical idea was this: information never really enters the black hole's interior. The event horizon itself, the two-dimensional surface, encodes all the information about the three-dimensional volume inside, like a hologram. Everything that falls in leaves an imprint on the horizon. When the black hole radiates, there are subtle correlations in the radiation. Information is encoded in the pattern of photons. Not obvious, exponentially scrambled, essentially impossible to decode in practice, but present. Think about it this way. Every object that falls into a black hole increases the horizon area. Jacob Bekenstein had shown in the 1970s that black hole entropy is proportional to surface area, not volume. This was curious? Entropy measures information, how many microscopic states correspond to the same macroscopic state. Why would a three-dimensional object have entropy proportional to its two-dimensional surface? Well, not why. That phrasing suggests it's coincidental. The holographic principle says that's exactly what's happening. Entropy depends on area because the information is stored on the surface. The surface area tells you how much information the black hole contains. When the black hole radiates, that information can leak back out through subtle correlations in the Hawking radiation. I had a devastating counterargument: the equivalence principle. General relativity's foundation is Einstein's equivalence principle. A freely falling observer experiences no gravity locally. Locally, physics looks the same whether you're in free fall or floating in deep space, far from any gravitational source. This means crossing the event horizon should feel smooth, unremarkable. Nothing special happens there from the perspective of someone falling in. But if information can't cross the horizon, if the holographic principle is correct and information must remain on the surface, then something violent must happen at the horizon. A firewall, an energy barrier, some physical mechanism that prevents information from entering the interior. This destroys the equivalence principle. And the equivalence principle is general relativity. You can't have it both ways. Either you save quantum mechanics by violating general relativity, or you save general relativity by violating quantum mechanics. That's the paradox. That's why we fought for 30 years. Not stubbornness, not ego. A genuine physical contradiction between our two most fundamental theories. In 2012, 4 physicists, Almehri, Marolf, Polchinski, and Sully, sharpened the paradox brutally with what became known as the AMPS firewall argument. The logic is airtight. If information escapes in Hawking radiation, the radiation must be entangled with earlier radiation. That's how information gets out, through quantum correlations. But quantum field theory requires that radiation just outside the horizon is entangled with its partner inside the horizon. Standard quantum field theory in curved spacetime. Here's the problem. Quantum mechanics forbids one particle from being maximally entangled with two others simultaneously. Monogamy of entanglement. If photon A is maximally entangled with photon B, it cannot also be maximally entangled with photon C. The mathematics doesn't allow it. So Hawking radiation cannot be both entangled with earlier radiation and entangled with the interior. One of these must fail. The AMPS resolution, the event horizon becomes a firewall, an energetic barrier. Anything attempting to cross gets incinerated instantly. Information doesn't fall in because you burn up first. This preserves quantum mechanics. It destroys the equivalence principle. It makes black holes inconsistent with general relativity as we understand it. I objected strenuously. This makes the physics at the horizon depend on the global state of the Hawking radiation that's been emitted over the black hole's entire history. An observer falling in shouldn't experience anything unusual based on what radiation escaped billions of years ago. Susskind essentially accepted the firewall, at least for old black holes. Young black holes, newly formed, hardly evaporated, should have smooth horizons. Old black holes, more than half evaporated, might develop firewalls. The transition matters. But here's what changed my mind. At a conference in Dublin in 2004, I announced that I'd been wrong. Information is preserved. I gave Preskill his encyclopedia. Not Susskind, I should mention, a bit of pettiness on my part. My new argument involved the topology of space-time. Event horizons are temporary features, not permanent structures. Quantum fluctuations of the gravitational field prevent true event horizons from forming. Information escapes through quantum gravitational effects that smooth out the horizon structure. The problem, my explanation didn't actually work. The paper I wrote was vague. The mathematical details were unclear. Even I wasn't entirely satisfied with it. Susskind certainly wasn't. The mechanism remained mysterious. I'd essentially said, unitarity must hold, therefore information escapes somehow. But that's different from proving how it escapes. It's like saying, I don't know the mechanism, but quantum mechanics must be right, so I'm changing my position. The fight didn't truly end. It just shifted. Where do we stand now? The consensus has shifted toward Susskind's view. Information probably escapes. But the mechanism is still debated fiercely. The leading candidates include holographic encoding on the horizon, which is Susskind's perspective. My own later work with Malcolm Perry and Andrew Strominger suggested soft hair on black holes, zero-energy gravitational perturbations that might encode information. Juan Maldacena and Susskind proposed connections between wormholes and entanglement, captured in the slogan ER equals EPR, Einstein-Rosen bridges equal Einstein-Podolsky-Rosen pairs. Then came the island formula in 2019 and 2020, a genuine breakthrough. Physicists showed you can calculate information in the radiation using a new prescription involving quantum extremal surfaces. The Page curve, the expected trajectory of information during evaporation, was recovered. Information starts escaping around the halfway point of evaporation. The mathematics matches quantum mechanical predictions precisely. But, and this matters, we still don't know where the information goes during the first half. Does it sit on the horizon? Does it exist simultaneously in both the interior and the radiation? Does space-time itself encode information non-locally? We've proved it works mathematically. We haven't proved we understand it physically. Actually, worse than that. The island formula works in simplified toy models. Two-dimensional gravity coupled to matter, anti-de Sitter spacetimes. Not in full four-dimensional quantum gravity in our actual universe. We've made progress. We haven't solved it. Why does this matter? Why spend decades arguing about information in black holes? Because black holes are the only laboratories where quantum mechanics and gravity both matter equally. In everyday physics, gravity is negligible at quantum scales. The gravitational force between two electrons is 43 orders of magnitude, weaker than the electromagnetic force. Quantum mechanics dominates completely. On the other hand, quantum effects are negligible at gravitational scales. Your trajectory, falling toward Earth, is determined entirely by classical general relativity. Quantum uncertainty in your position is irrelevant. But at a black hole's event horizon, both effects are comparable. The gravitational field is enormous. Quantum effects near the horizon produce radiation. Nature doesn't let us ignore either theory. Whatever resolves the information paradox will reveal the nature of quantum gravity, the theory that unifies quantum mechanics and general relativity. String theory claims to resolve it through holography and the ADS-CFT correspondence. Loop quantum gravity claims discrete space-time structure prevents singularities. Various approaches to quantum gravity stake their credibility on solving this paradox. We have proposals. We don't have a decisive test yet. But the fight revealed something deeper. Susskind introduced a concept called black hole complementarity. The idea is this: information appears destroyed to an observer who falls into the black hole. They cannot cross the horizon, see the information continue inward toward the singularity, experience it being destroyed. Information appears preserved to an observer who remains outside. They see subtle correlations in the Hawking radiation that, in principle, encode everything that fell in. Both perspectives are valid. Both are correct descriptions of the same reality. They're never directly comparable because you can't be both inside and outside simultaneously. Like quantum measurement, observer-dependent reality. I hated this when Susskind first proposed it. It seemed like a philosophical escape, not a physical solution. But it might be correct. Quantum mechanics already has observer-dependent outcomes. The measurement you make determines what you see. Perhaps the description of space-time is observer-dependent too. Not many worlds, different observers experiencing different realities. Many descriptions of one reality, depending on your reference frame. Curiously, this fits with the holographic principle. The three-dimensional interior and the two-dimensional boundary are complementary descriptions, different mathematical formulations of the same physics. We started with a simple question: does information escape from black holes, or is it destroyed? 30 years later, the answer is probably yes, it escapes. But we don't truly understand how. The fight revealed that black holes expose a fundamental tension between quantum mechanics and general relativity. Both theories work extraordinarily well in their domains. Both have been tested to remarkable precision. But they give contradictory predictions at the event horizon. The resolution requires new physics. Quantum gravity, a theory we don't yet have in complete form. But here's what I think the real question is: not whether information escapes. The real question is what information even means when space-time itself is quantum. What does it mean for something to exist inside a black hole when inside and outside might be complementary descriptions of the same thing? When the distinction between observer and observed becomes ambiguous at the Planck scale? That's a different problem entirely. I've got to stop somewhere, though I suspect we're still missing something fundamental about the nature of reality at this level.